All right. Classwork 3.2. Here we go. Some of this is kind of redoing what we did yesterday. Because yesterday I was focused on you being able to figure out what size a logarithm was, what number did it represent. Today we're going to look at the graphs that the logarithms create. So like yesterday, we're going to fill out a table of values for 2 to the x. When x is negative 2, this becomes 1/4. Is it okay if I do it that quickly? When x is negative 1, 2 to the negative 1 is 1/2. When x is 0, we get 1, and then 2 to the 1 and 2 squared. For the inverse function, if my function is 2 to the power of x, then when I write the inverse, it's log, a subscript of a 2, and then back to the same line as log, the input for variable x. And all you're going to do is take these x's and y's and swap places. So you have 1/4 negative 2, 1/2 negative 1, 1, 0. Okay. Now, you're going to go down to the graph and you're going to plot these as points. And I actually want you to graph both of them. If you have color capabilities, different colors that you can use, I'm using blue for my 2 to the x points, and I'm using red for my log base 2 points. And I'm going to shrink that down a bit so I can see both at the same time. I'm going to start with this one. So for the exponential function that you should be familiar with, negative 2 1/4. I just wanted you to draw that. Thank you. I'm annoyed with my technology. It's not doing what I'm asking and what I'm wanting. There you go. Breathe. Negative 1 1/2. 0 1. 1 2. 2 4. And then I'm going to draw what I know the exponential graph will look like. Do you remember that it asymptotes over here? And do you feel very familiar? And I would really appreciate webcams being on so that I can see that you're working. Perhaps I can figure out how the whole whiteboard thing works and I can see a bunch of whiteboards with you working. We'll see if that can be something that happens. But I need to see individually that you are all actually participating and working. Now, the next thing I'm going to do is I'm going to graph log base 2 with an understanding that inverses reflect over y equals x. So I'm going to draw first a little dashed y equals x line. There we go. And then as I plot these points, all they are reflections of each of these points over y equals x. So I'm going to change my color to red. And I'm going to plot when x is 1/4, y is negative 2. When x is 1/2, y is negative 1. When x is 1, y is 0. When x is 2, my y value is 1. When x is 4, my y value is 2. And now, the exponential graph is asymptoting over here. Listen carefully. Over here, the y values are positive, while x is heading down toward negative infinity. I'm going to swap what I just said with x and y. Again, I'm going to repeat what's here. What's here is all of my y values stay positive near 0, while my x is heading to negative infinity. So instead of saying my y values are positive, I'm going to say with the logarithm, my x values are positive, and they are heading towards 0, while y is heading to negative infinity. I have a vertical asymptote with my log graph. Now, the funny thing about log functions is if they are the inverse of exponential functions grow faster than, way faster than x squared, x cubed, any of those. A logarithm has to pull it and rein it back in. A logarithm grows really, really slow once you get out a little bit. And a lot of people will accidentally think that they asymptote when they look at them out here on the right side, if I were to look at the full graph. But they don't asymptote. They continue growing. They're like, ooh. Have you ever seen pictures from Hawaii is what I'm thinking, where people have videotaped lava coming toward their house that cannot be stopped? It's slow, but they can't stop it. That's a logarithm and the way that it grows. It's very, very, very slow. Did you? Hopefully lava did not come to your doorstep. So you need to understand and learn about the graph of the logarithm. The domain of your logarithm is 0 to infinity. Okay. You don't want to work with me, do you? No, you don't. Okay. Technology, I am unhappy with you. You can take your technology back. I am done with technology. Okay, I think that's back where I needed it to be. Okay. Your domain will not include 0 and will go to infinity. Keep in mind that domain is asking about what x values does this graph exist in. You cannot put 0 into a logarithm, but you can put any positive number into the x of a logarithm. Now the range is looking at vertically, where does this exist? And you can see the negative infinity down here. And this does continue to grow upward. It does head to positive infinity. Do you recall that exponential functions have domains negative infinity to positive infinity for where their x's exist? And do you recall that their range is only positive numbers 0 to infinity? Anytime you have a pair of inverse functions, they swap their domain and range. So I want you to take a good look at how these are swapped domain ranges. On the exponential graph, you had a horizontal asymptote. The equation is y equals 0 for that horizontal asymptote. The intercept on your exponential graph is a y-intercept, so it is the point 0, 1. Now I'm going to go back over to the logarithm. The asymptote on the logarithm is not horizontal, it is vertical, and a vertical line has equation x equals. So there is a vertical asymptote, but it's only effective on the end where x is negative. And you have an intercept that all log functions will go through, and that is the x-intercept of 1. And I want you to see how the intercepts are swapping. What was a y-intercept of the exponential graph is now an x-intercept on the logarithm graph. Now let's do this again for 5 to the x. Is everyone working with me? Because if you're doing this with me, then you're able to turn it in when class is over and get a bunch of points. What in the world is going on in chat? I don't even want to know. Okay. So 5 to the negative 2 power. Hopefully you remember 1 over 25. 5 to the negative 1, 1/5. 5 to the 0 is 1. 5 to the 1, 5. 5 squared is 25. So if I'm going to look at the inverse of that exponential function, we call it log base 5 with a subscript of a 5, and then the input x goes back on the same line as the LOGs. I'm going to take every one of these xy pairs and swap them. So I have 1 over 25, negative 2. 1 over 5 goes with negative 1, and so on. And just like before, we're going to plot these points. But, okay. Oh, okay. Let's get away from the lava flow. And everyone in Hawaii learns that in elementary school. Using a garden hose is how you stop lava from reaching your house. What?
Why would we want to go away from the danger jelly?
Okay, you know what? I'm not going anywhere in that vicinity. I'm coming over here. I'm ignoring. I'm going to plot the points of this logarithm. 1/25 is near impossible to plot as an x-coordinate. So basically, it's pretty much, it doesn't like it when I hold the pen there too long. So it is even closer than I can draw. Then I have 1/5 for an x-coordinate goes with negative 1. I can kind of draw that. 1, 0, very important point. 5, 1 is another very important point, and I'm not even going to be able to plot the last one. Your logarithms can only have positive x's, at least when you draw a parent graph. And looks about like that. Then you're also drawing the exponential function with it so that you can see this inverse nature. So you're going to go through and you're going to plot these points. And to save a little bit of time, I'm going to go over to the answers to show you those. There we go. So this is what they should look like. So realize that if the base of your logarithm changes, look at these two graphs and see that it kind of makes it look like it's multiplied by a different number. It's close to doing that. But all of them go through the point 1, 0. As far as domain and range and all the asymptotes intercepts go, this is identical to the previous problem. So every one of your log functions as a parent graph. Wait. Okay, yeah. Wait, no. What did I do? I wrote that wrong. Yay! I need to fix that now too. So the domain should say 0 to infinity. And I need to remind myself to change that. That is classwork answers 3.1. And then where am I going? No, 3.2. Okay. So the domain and the range swap for the exponential versus the logarithms. Now, for a generic log function where the base is greater than 1, you need to know this. You're going to be graphing parent graphs. Every single logarithm goes through the x-intercept 1, 0. And it helps if you remember that that's a reflection of the y-intercept that every parent graph has with exponential functions. Now, if I try to plug negative numbers into the x of a logarithm, your calculator is going to go, no. Just plain no. These are going to give you undefined, and I want you to be aware of that. Even if you try to find 0, if you plug 0 into logarithm, you will get undefined. There are 2 important points I want you to find for every parent logarithm graph. 1, 0 is one of those points. For the other point that you want to be aware of, if I plug b into x, do you remember that this is asking what is the exponent for b to the power of that will give me an answer of b, and that number is 1. Now, whatever b happens to be, let's say it's here. Then, oh wait, hold on. I just did that wrong. My apologies. Let me start that again. B is the input. So wherever B happens to lie, you're going to get a y value of 1 out of that B. These are the 2 points that I want you to plot every time you have a parent logarithm graph. Then you will remember, hopefully, at least, that this asymptotes, if I look at x going from 1 to 0, it's just getting closer and closer to the y-axis. And then when I draw this direction, it grows, but really, really slowly. Now, what are important features of all logarithms with bases greater than 1? The domain is 0 to infinity, not including the 0. The range is always negative infinity to positive infinity. The vertical asymptote of the parent graph is always x equals 0. And I want to make sure that you know that as x approaches positive infinity, f of x is approaching also a positive infinity. But what I think you should also be aware of is that it grows slower and slower and slower. I like to think of logarithms as like some cute little comic thing that I saw a while ago that had, what was it? It was a snail hitching a ride on a turtle and going, wee! That's a logarithm. Very, very slow. Thinking that a turtle, wait, why did you put, okay, B, I put it between 3 and 4, not for any particular reason. We're working with B being any number that's greater than 1. So I could have put B anywhere along here. What I want to get you to see is that while every single logarithm has this x-intercept to plot, you can plot a second point to distinguish it from other log graphs. And that second point is whatever the base of that logarithm happens to be, the y value will come out as 1 for that point. And in the answers I just kind of threw it around there. So hopefully what you're understanding is that every parent logarithm graph that you draw, you are going to put 2 points, 1, 0, and whatever the base number is, comma 1. Okay. All right. Then let's see how you are doing. This is the last bit for the classwork. So I want you to sketch the graph of log base 3 of x. Everybody should be graphing that right now. And eventually I want to figure out how I can see your work on your little square. I know the technology is out there. It's just a matter of me learning the technology. Actually, question, do any of your teachers use something where they can see what you are working on? Okay. I think that's going to have to wait until you guys get those Chromebooks that the district promised that they said they were prepared. Oh my gosh, I'm sorry. Okay, I need to take a moment to show you what annoys me. I'm going to show you what annoys me. Right here, prepared. If they were prepared, you would have Chromebooks with a stylus before school started. Oh, you're right. Okay. So, log base 3 of x, have you graphed it? I'm hoping that you are graphing it ahead of me and that you're not just waiting for me to do something and then copying it. For log base 3, you need to plot the point 1, 0. Yeah. Then, because the base is 3, what is the second point? Let me see in chat if any of you can tell me the second point. Because the base is 3, what can I plot? Excellent. I can plot the point 3, 1. Then when you go to graph the logarithm, you want to remember that it asymptotes and then it grows slowly. The x-intercept of the parent graph, 1, 0. The domain of the parent graph, 0 to infinity. The range, negative to positive infinity. And the vertical asymptote, is x equals 0. Now, do you remember how multiplication outside the function, how does it affect the graph that you see there? And what does it do to the y? There we go. It stretches. It's going to do that operation, multiplication by 2, to the y values that you have there. Now, this y value is 0, multiplied by 2, still 0, x coordinate 1. This point right here, the x coordinate is 3, the y coordinate is 1. The y coordinate 1 is multiplied by 2, but I'm going to keep it located at x equals 3. And by you plotting those 2 points, I'm watching that you understand that it's stretching it. But other than this point, it's really hard for me to see that you have stretched it, because this isn't a graph. There we go. This isn't a graph that really shows it's stretching all that well. It's important that you know that with that multiplication, all of these are the same. So if you're working with a computer, you can just do copy paste. None of that changes with the multiplication. But it can change with the addition subtraction. So I want to point out to you that C is starting off with 2 times log base 3, which means this graph right here. X is having 5 added to it, and outside the function, we are adding 1. What does this addition of 5 tell you to do to the original graph, or to the previous graph? Yep, we're going to move left 5 because we do the opposite operation when it's with the x. It says add 5, we say no, subtract 5, go left 5. But with the plus 1 outside the function, that's going to move it up 1. Good.
X is something that would probably do tax evasion.
Okay. Now, here's what you need to do to be accurate. You need to take the points where they were, these 2 points, move them. This point is at x equals 1. So starting at x equals 1, in fact, I'm going to do this. I'm going to draw a green point for my starting points. These are the points that I'm getting from 2 times log base 3 of x. And then I'll put in red where they move to. So left 5, up 1. Over here, left 5, up 1. Now, the vertical asymptote was at x equals 0. If I move this graph left 5, that is going to move the asymptote over to -5. Does up 1 affect it? Will moving the graph up 1 make any changes to the vertical asymptote? And And hopefully you realize the answer is no, it won't make any changes. Good, thank you, thank you. So one thing that you want to be aware of is the horizontal shift is going to tell you exactly where your vertical asymptote is. Do you remember that with the exponential graphs, the addition subtraction outside the function told you where the horizontal asymptote was? For logarithms, it's the horizontal translation. I'm seriously getting annoyed. Okay. So I'm going to draw a little dashed line here at -5. In fact, in the future, what you may want to do is when you have a translation of a graph, draw the asymptote first. The asymptote is always the number that makes the inside of the logarithm turn to 0. And now I'm going to graph this function, or at least try. The domain is now from -5 to infinity. The range will always be negative to positive infinity, and my vertical asymptote moved over to -5. So that's the end of classwork 3.2. You have due today by midnight this classwork and homework 3.2 and the answer corrections on 3.1. Now, I asked you before I started the classwork if you had questions on 3.1. I'm going to stop sharing this